Okay, thank you. So yes, I will talk about sequential prediction problem in a kind of general framework. But on the other hand, I will keep in mind in the end the application of the method I will present today to training large-scale neural network, probably in a way that MT Can already talked to you actually about, because I think that his lecture was Monday or yesterday. So actually it will seem quite different in the beginning, maybe a bit abstract in the beginning and a theoretical approach, and you might not really see the relevance in practice. But hopefully, if I reach the end of the presentation, I will be able to make the connection with the nice methods presented by MT. Okay, so just a slide that I will skip very fast because there's not a lot of relevant information on it, apart from the address of my webpage and my email address. So if you want to check the papers related to what I'm talking about today, it's on my webpage. And if you have any question, I will be happy to reply to emails tonight or tomorrow or whenever you want. Okay, so now I'm going to explain what I mean by a sequential prediction problem. And to start with, I will focus on a sequential classification problem. So it's a problem where actually you will have to classify objects. But the point is that you're not given a whole data set to learn a classification rule. Instead, actually, you will be given objects sequentially, and the label will arrive sequentially. And you have to learn to predict each time actually the next object as well as you can, okay? So I mean that, for example, you start with just one image and I ask you to classify it. And if you're using a statistical method, well, you just don't have data actually, so you don't know how to classify it. You can make a kind of random guess, but then I will tell you the truth. Okay, this image was number 3, for example, and then I give you another image. And this time, maybe you can make a more sophisticated guess, even though your experience is quite weak still. But you make a guess, y2 hat, and then I reveal you the true label. Now, this image was not a 3, it was a 5, and we carry on. Okay, so actually, it's in some sense, you can imagine that you're using your favorite neural network to try to classify images. But instead of training it once and for all on the data set and then using it in a real life application, you want that it carries on training itself. Each time it sees a new object, it makes a prediction and then it can be corrected and then you can learn more actually, okay? So the point is that if we want to play this game in a sensible way, actually the objective will be to try to learn to predict the label as soon as possible. And so actually, if I stop the game at any step, any time step, capital T, then I want that the number of mistakes, that is the number of times that yt at was not actually equal to yt, is as small as possible. So of course, this function will be increasing, but I want it to be increasing as slowly as possible. Maybe it would be nice if it could become constant at some point. Okay, you will see that it's on the contrary to like many analyses of statistical methods. Actually, it's quite nice because there is a theory on how to perform such predictions that actually holds without strong assumptions on the data. We don't have to assume that the data are IID from a probability distribution or something like that. It's possible to provide like nice guarantees with almost no assumptions on the data. Okay, so I'm going to explain the framework first before going into details, but just I want to mention these 2 books because, well, when I started actually doing some research in statistics and machine learning, I was not aware at all of these online methods. I learned from these persons actually in summer schools and reading their books, and these books are quite amazing actually. So if you don't know what to do in the next few weeks, just to read these books is really, really entertaining. It's very nice. Okay, so I will start by going deeper into the definitions and explaining the framework. So it will be as follows. So just as before, I will use xt for the object that is given at time t, okay? And yt will be the corresponding label, which can be 0, 1 in the case of classification, but of course, as usual, it can be a real label in the case of regression. And actually, most things I will say today hold for a general label space. You will have to perform a prediction, yt hat, Okay, so yt hat, actually you have to perform yt hat just when you are given xt, but before knowing yt. And then I use the notation, I think it's a classical notation, you probably know it or something similar, but L of yt hat and yt is the loss that I incur when I make the prediction yt hat and the truth was actually yt. So for example, in regression, of course, you have like the least square regression or least absolute value regression. In classification, usually you take like 1 or 0, depending on the fact that you have a mistake or not, okay? I'll come to this later, depending on the context, actually. So the point is that usually when you think of this context, you think that you are given a nice IID data set, x1, y1 to xn, yn, okay? And actually, the point is that it might be that in a sequential framework, the observations are not independent, okay? It depends actually on how the data is collected, but I mean, if you try to predict something like a time series, for example, of course, then the data will usually not be independent. So the algorithm I'm going to present today, you will see, are robust to an extreme range of situations. Of course, the usual case we have in mind when we have a statistics background is that yt is actually a function of xt and of some IID noise. This is fine. But actually, it can also be a function of the past. Okay, this is the situation we have in mind when actually we are trying to predict yt that would be a time series. Okay, but actually the point is that what I'm going to present today allows even to go a bit further. For example, what happens if you don't have all the variables, if you have omitted variables, zt, okay? Well, of course, like there's no miracle. If there are important variables zt to predict yt and you don't have them, then of course your predictions will not be accurate. But still, I would like the prediction to be as accurate as possible without knowing zt. And this is something that we will learn to do together. Okay. Something that can be actually quite annoying when you have a time series is that the data is not only not independent, but it can be also not identically distributed in the sense that there can be a drift in the link function between y and x. So it can be that this function also depends on t. This is not a problem. And there is something worse, actually, is that sometimes you can have to predict something, and it might be that the truth will actually depend on your prediction. Okay, look at this. Remember the setting. You try to predict yt by yt hat, and then actually the true yt would be a function of your prediction. It's like, it can sound unrealistic, but if you assume that actually you are a government and you are trying to predict what will be the state of the economics next year, then usually what you announce will have a lot of influence on what will happen in real world. It doesn't mean that it will be exactly the same or that it will be exactly different, but still, if you say we are confident that this will happen, then sometimes people will trust you and it will improve the state of the economic or that kind of things. Or you can just think about the current epidemic, actually. And when you say, well, tomorrow there's going to be a lot of cases, then people stay at home because they are scared and there is no cases. But if you say tomorrow everything is fine, then everybody goes to party. And then the next day there are many, many cases. So sometimes you make a prediction and it will have an influence on the truth, okay? Actually, even when this happens, the theory that I will present to you can still be applied, okay? Now, actually, you can have a kind of combination of all the previous situations where yt would be a function of the past, of the prediction, of some noise, of some unknown variables, and will be non-stationary, okay? So I'm going to explain how to deal with this later. Well, still, first, a little remark. Of course, when I say that it's possible that in real life, what will be the truth is a function of what you predict, of course, in the worst possible case, it's absolutely not possible to do anything against that. Okay, so I'm going to propose you a game that is not very relevant in practice, but it's just something that shows the limits probably of what I'm trying to explain to you. Just assume that at time t, so you know the objects x1 to xt, and you know the labels y1 to yt minus 1, you are asked sorry, I just forgot to mention one thing. Yeah, excuse me. Actually, I was thinking about the next slide. So yes, actually, so the prediction that you do first, actually, yes, sorry, they must be, of course, they must depend on the past observations, and obviously, if possible, it would be nice that you don't have to store the whole data set, but it's something that sometimes cannot be avoided. It must be computationally feasible, and we will see, actually, I will explain this sentence later, we can use expert advice, which means that we can use maybe some predictions made by someone else. I will explain this concept later. Sorry, yeah, I was saying that there is a limit in the sense that if I propose you the following game, at time t, you have to predict yt, and you actually make the prediction yt at. And then actually the true yt, well, it's just decided in the following way. It is exactly the opposite of what you said. Okay, so actually I'm asking you to classify objects. And the point is that I'm cheating in the sense that I don't know the label of the object. I did not decide it yet. So I ask you to make a prediction. And when you make the prediction, then I decide that the real label of the object is exactly the opposite of your prediction. Okay. Of course, if I ask you to play such stupid game, well, actually, I should not say that the game is stupid, but it's clearly biased in my favor. So actually, in the end, you will make a wrong prediction at each time. Okay. The point is that, of course, in such a situation, it's not possible to do something sensible, but it's rarely the case that you will have to play such a game. So it's possible, actually, that in some sense, the data is nice, it's easy to predict. Sometimes it's less nice in the sense that the truth can actually be, in some sense, a function of your prediction, but you will never reach this kind of extreme case where the truth is simply the opposite of what you predict. So in some sense, the real world is kind of in between the nice situation where the data is IID from a very nice model that you know, and everything is just like in the most ideal statistical lecture, and the adversarial situation, which is described here, where the data is completely adversarial and absolutely impossible to predict. Okay? So, the idea will be to propose to you some algorithms that are able to adapt to this level, like somewhere in between the very nice setting and the impossible setting. You have the real world somewhere, and the algorithm will actually guess to some extent what is the usefulness of the model to make prediction. As I'm going to present a short example in 1 minute, I just want to mention first, before I carry on, I tend to be extremely focused on what I say and not on actually what happens on my laptop. Like, for example, if you write a message on the chat box. So if something is unclear and if you have a question, please interrupt me, ask Rodrigo to interrupt me and ask your question. I would be happy to answer your question rather than to carry on with something that would not be clear for everyone, okay? So, as I was saying, like there are two extreme situations, the completely adversarial setting and on the other hand, the very nice setting where everything is in a model that we know, etc. And I would like to focus on this case just for 1 second, actually. So just for 1 second, I'm going to consider here, just the last 3 lines of this slide, sorry. The situation where the object x1, x2, etc., or whatever images that you want to classify. But actually, we know that there is a set of function f. Let's say it is finite, just for now, it is finite, okay? And there is actually the constraints that the yt's are exactly equal to one of the f of xt's for one of the f's in the model, capital F. Okay, so this is the situation where actually it's not an adversarial situation, it's exactly the situation where it's nice. Actually, you propose a model, capital F, and you know that the truth is somewhere in the model and you just have to find the truth. And then you will be able to do perfect predictions, okay? But actually the point is that to try to understand the strategies in this very simple game will give us some insight on how to proceed in the more general case. So I'm going to propose a first strategy which seems quite clear. I recap. I have m functions. So now I should use maybe index, okay? F1, F2 to Fm. And then I have a sequence of objects, x1, x2, x3, that are revealed sequentially. And each time I have to predict the corresponding label, and then the true label will be revealed to me. But I know that the true label is constrained to be exactly equal to fi star of xt, where I star is a fixed index in 1 to n. Okay? So what seems natural is that in the beginning, I know that all the functions in this set are potentially the best one, the true one. But then actually what I will do is that each time I observe that a function makes a mistake, I will remove it from the set. And then I know that at some point, I will probably end up with just one function, and I know that this function will be the right one. But remember, I'm not only asked to perform, like to find a good function, I'm asked to perform predictions as well, sequentially from the first step. So what I propose then is that until this set is not reduced just to a singleton, just to a single point, then what I can do is just to choose one of the functions in this set and use it for prediction. Okay? So say I start with an index I equal to 1 arbitrarily, and at each step, I predict yt hat by my current index, fi of t of xt. And then actually I update my set of functions, which means that actually I only keep the functions that did not make any mistake at that step. So recursively, actually at time t, I only have the function that were always correct, that predicted y1 correctly, y2 correctly, etc., etc. So then, of course, it might be that the function it that I'm using now is removed from this set if it makes a mistake. And then in this case, I choose the next possible one. So it's just arbitrary. I have to choose one function in the set 1 to m. Then I choose the one corresponding to the smallest index. Okay? So if you use this strategy, then actually what happens is that whatever how long the duration of the game, you might play an infinite number of rounds, you will never make more than n-1 mistake. This is just absolutely trivial because like the worst situation is the case where you use f1 for prediction, but then it's wrong, so you switch to f2. And then you use f2, but just in the next round, f2 is wrong, so you switch to f3, etc. And then at some point, you will reach fm. And well, if you're not lucky, it might be that it's just the last function fm that is the best possible one. Okay, so actually you might switch n-1 times, which corresponds to n-1 mistakes. Okay, so I just propose actually a kind of toy example to explain how this algorithm works. And I have to apologize because this is actually an example related to the French soccer team, and it's an example that I prepared for a talk in front of French students, and I did not have time to adapt it to the Russian team, so I'm sorry about that. But anyway, so the point is as follows. You just imagine that you have automatic functions trying to predict what will be the outcome of a game between the French team and another team. Okay. In practice, I mean, I know that some people are paid to make some predictions. And here again, I'm sorry, because actually for French students, these guys are quite famous journalists to make predictions on TV before every match. They say, well, the team is going to win or to lose and blah, 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 blah. You probably don't know them, but I'm sorry, just believe me, these people are actually known by some people. Okay, so just assume that each of them come with a prediction before a game, okay, in the World Cup. Of course, I just want to do some binary classification, so I will switch the score 2-1 will be a victory, and say I just want to make a discrimination between victory or tie and defeat. Okay, so I will just have W for win and DL, which stands for tie or defeat, lose. Okay, and then the point is actually that this person, even if you don't know them, you actually know that they don't satisfy the assumptions I gave to you before, because one of the assumptions was that actually, sorry, here, one of the function is always right, and I can tell you that actually, even though I'm not a specialist of football at all, but I know that these people are quite often wrong. So actually, the point is that we all hope that AI is going to do things quite well in the future. So we're going just for this toy example to assume that there is actually a super machine that makes perfect prediction, because this machine knows everything about the weather, about the health of the players, it knows everything. So it will make perfect predictions. And we play the strategy I proposed to you. So actually just before the first game, some people predict a victory, others predict another outcome. So actually I just decide to use one of the experts, one of the predictors. So when I underscore the letters, it means that this is the person I decide to follow. And then actually it appears that the person is wrong. So red here means correct, means wrong, sorry, and green means correct. So it means that these people were correct. And so actually this function and this function are removed from my pool. And I end up with only 4 functions that will make predictions. And here again, I have to choose one. I can choose this one, for example. Here again, I'm wrong, okay? And you carry on. And in the end, well, after here you see 5 games, the pool of experts, the pool of predictors is reduced to just one. So which means that from now, I will always use it, and I will always use the one that makes no mistake. Still, I made 1, 2, 3, 4 mistakes, okay? According to the previous theory, I can make at most 5 mistakes. I made 4. Well, okay, not so good. Now, sorry, maybe this seems completely trivial to you, actually, but we're going to move now to more sophisticated things. Before I proceed to the next slide, I would like to ask you, do you have any idea on how to improve on this strategy? Is it possible, actually? You know, there are m functions. One of them is always right. The other might be right or wrong. Is it possible to propose a prediction strategy that will make less than n-1 mistakes? So, sorry to be annoying, but I really want someone to try to propose an answer for this. What is your intuition on this? Do you think it's possible or not? Or do you have any idea of a method that could perform better?
Is it without additional assumptions, Pierre?
Without additional assumptions.
Someone proposed to use random sampling. Another person says, can we select the candidate functions according to some probability?
Mm-hmm. Okay, so actually it's correct, even though it's not the method I'm going to propose, but because actually it's, in some sense, you can perform random sampling, but if you want, you can also perform random sampling of 2 functions, random sampling of 3 functions, and in the end, if you sample enough, what can you do with many functions? Well, you can make them vote. Okay, so which means that you can make aggregation instead of sampling. Okay, but indeed it's the right idea, and quite surprisingly, because my intuition when I saw that first, I always have wrong intuition actually, but when I saw that, I was like, well, obviously it's not possible to do better than this, and it is actually. So the idea is just, sorry, you just have to skip this. The idea is just as follows. I keep the same idea. I have a pool of experts, and I have no more information that they were always right or they made a mistake. And when they made a mistake, I know that they are not the correct one, so I can just take them out of the pool. But what I will do is to predict at each step by a majority vote. So I just take all the experts that are still possibly the best one, and I make them vote. And then I update exactly in the same way my set of predictors by removing the ones that were wrong. Okay, so the point is, in this case, it's quite interesting because if you make the experts or the predictors vote, you don't make better because the majority is right. It would make no sense because here, in this case, actually, I have no assumptions, and it might be that the majority is not right. I said that one function is right, but it might be that all the others are always wrong, actually. But still, you will win something. And the reason why, actually, is simply that assume that you are wrong. Assume that at step T, your prediction is wrong. It means that the majority vote was wrong. So it means that the majority of the members of this set were wrong. So it also means that at the next step, the majority of the function will be removed. Okay? So in the previous algorithm, when you made a mistake, you were sure that the function that you used made a mistake and would be removed from the pool. So the set would maybe decrease just by 1. But in this case, where you make a mistake, then actually you're sure that this set will be at least divided by 2. Okay, which is quite important, because if you take a set of size n and you divide this size by 2, and then by 2 again, and then by 2 again, and you know that you have to stop when you have one function left in the set, well, you cannot do this process actually more than log of m in base 2, actually. Okay, so it means that using this voting strategy, simply because when you're wrong, you know that actually, well, the next step, you will remove at least half of the functions. Then actually the number of mistakes that you will do will be smaller than the log of m. In order of magnitude is the log of m and not m. So it's quite important actually. And interestingly enough, we will see that such aggregation strategies are indeed sometimes optimal to deal with such sequential prediction problem, even when we remove this absolutely, completely unrealistic assumption that one of the predictors is always correct. Okay. Now, about actually your proposal, you said we could perform random sampling. So it's, if instead of a majority vote, you perform random sampling, well, with large probability, you will pick a member of the majority. So you can derive similar bounds actually in expectations or with large probability. So it works in the same way, and it's also a good idea. I just chose to focus on aggregation in this slide. Okay, so this algorithm has been known well. Yes.
One participant asked, with the naive strategy, do we only remove one expert per step, even if several experts are wrong?
No, we remove all the experts that are wrong. Okay, you see here, 2 were wrong, and I removed 2. The point is that in the worst possible case, it might be that only one expert is wrong at each time.
And if we do not have an ideal predictor and all the experts are wrong?
Sorry?
So what if we don't have an ideal predictor and all the predictors will all the predictors be wrong?
Exactly. This is the realistic scenario. I said that just for 10 minutes, I'm dealing with this unrealistic scenario where one of the experts is always right. Of course, this is an assumption I will remove soon. And we will see a strategy that is inspired by this aggregation strategy that will work even if all the experts are wrong. The point is that if they are all wrong, you don't target the true one because there is no true expert. You just target the best one. So you cannot remove someone forever. And we will see that there is a slight way to adjust this algorithm so that it works in this case. But this is essentially what I will talk in the next 30 minutes, actually. Okay, so I will just be quick on this, but I just used the halving strategy. So by the way, so I was just mentioning the halving name. So this name was proposed for this algorithm because of what I said, because each time there is a mistake, you remove half of the set of predictors. I just choose on the same set of predictions, actually, this algorithm. And here you see that, for example, the majority is W, okay? And in this case, actually, it's right. So you make no mistake and you end up with only 4 predictors, etc., etc. You can check all the steps if you want later with the slides. But in the end, you end up with exactly the same output in the end, which means that at step 5, sorry, you know that classifier 5 is the best one. But until then, actually, you're right on step 1, you're right at step 2, you're right at step 3. And here, only step 4 was wrong. And just because actually in this case, there was no majority, so I just draw randomly, actually. So, and the point is, more importantly, of course, I proved it, even though the proof was quick and not written down, but I hope you understood the argument. I proved that halving has a better bound than the naive strategy. But I mean, if you're not convinced by this example and think that I made it up, then actually you can just use any other set of votes. And this one is important because it's just an illustration of the fact, what happens if the majority is wrong. And once again, the halving strategy is a voting strategy, but it does not rely on the fact that the majority is right. Here, the majority is wrong, okay? They all predict a defeat. And the point is that the strategy will choose defeat, but the truth is a victory. And of course, you make one mistake, but at the next step, you almost have no experts left. So you're almost done, actually. You know that you will not make so many mistakes, okay, until the end of time. So here, same, you make at most 2 mistakes, and then actually you know which one is the best one. Okay, so before, sorry, maybe I talked too much about like kind of philosophical considerations before switching to the technical part. I will come to the technical part in a few minutes, but I would just like end up with a recap on what I said before. As I have I will have from now no assumption on the data, you have 2 extremes. The extreme situation is when you're playing against an opponent with cheating and which can manipulate the truth. So people call that playing against the devil. And then you cannot win against the devil. This is the idea. And then in this case, nothing is possible. Whatever you predict, it will always be wrong. On the other opposite, you have the case where you have a true model. The point is that in real life, it's somewhere in between these 2 situations, I think. I don't know a model that is absolutely exact. And on the other hand, I don't know a situation where it's absolutely impossible to make predictions. So our objective will be to propose strategies such that we will have the following, actually. The sum of the mistakes that we make will be as small as possible, okay? And actually, we will see that we will, given a set of functions f, a set of predictors f, we will split it into 2 parts. A kind of incompressible mistake. That will be the mistake made by the best predictor in the class of function f. Okay, so I hope this answers at least partially the question, what if there is no good predictor? If there is no good predictor, I will not target 0 error. I will just target to make as many errors as the best predictor, the best possible predictor, okay? And once again, for example, in classification, when the loss is 0 or 1, and in the worst case, there's nothing to do. This will always be equal to t. And it's not interesting, it's not a relevant game, there's nothing to do. And in the ideal case, where one of the functions in the model is absolutely correct, this mistake will be 0. Once again, the truth is kind of in between. And the idea is that you don't want to assume where it is in between, but the algorithm must be able to know it and to adapt it to the current situation. And of course, as you are learning, in the beginning, you will make more mistakes than the best function f. So you will have a residual term. And all the theory I'm going to propose to you now will be like to try to propose a strategy, YT hat, that will make this term, BT, as small as possible. Okay, so actually, the way that these kind of bounds are usually written in papers is as follows, actually. So the sum of mistakes you make is as small as the best possible sum of mistakes using a function in the class f plus a bound. Actually, people usually move this term to the left-hand side. So they tend to write this, actually. The excess error, the difference between the error you make and the best possible one is smaller than the quantity b of t. And the terminology for this, as you can see from the title of the slide, is called the regret, because actually it's how much you regret not to have used the best function f since the beginning. Of course, you cannot regret it because you did not know it, but if at time 50 now you know which function is the best, then it's the price you pay for not having known it since the beginning, okay? So the idea is that, of course, in order to improve on what happens with respect to random drawing, actually, the regret, if you propose a regret bound, actually, it must be a small o of capital T. It must be small in front of T, because this is a non-trivial result. Otherwise, you can just like propose a constant prediction, and a constant prediction will make a constant mistake, and which will be, in this case, actually, the regret will be proportional to T. So it's like trivial strategies reach a regret that is of the order of T, and you want to improve on this, okay? And what we will see, so this is what I'm going to talk now, how to build non-trivial strategies. We will see that with absolutely no assumptions, it's not possible. But if you have a bounded loss function, in the case of classification, for example, then a randomized strategy will always help you to reach a regret of the order of square root of T. And if you want deterministic strategy, it's possible, but you need to have more assumptions. For example, you will need a convex loss function. Okay. In the same way, in the same spirit, actually, it will be possible to improve on the regret bounds in square root of t, to go to regret bounds in log of t, or sometimes even on the order of a constant. But in this case, also you need more assumptions on the loss function. Okay, so basically classification, so bounded loss function, no assumption, square root of t with a randomized strategy, but deterministic strategy or faster rates, in the sense that, sorry, faster rate is maybe not the adequate term, but a smaller regret, then actually this is possible, but then in this case you need more assumptions. Okay, and I will skip this because I don't want to lose too much time on just this blah blah that I prepared, but actually I think that many people like tend to oppose actually machine learning to modelization. Like machine learning is prediction and it is opposed to modelization. But the point is that if you want to perform accurate prediction in economics, physics, epidemiology nowadays, then actually, of course, you need to have a good class of functions f here. Like the point is, in some sense, that machine learning would be like to try to make the term b of t as small as possible, but it does not make sense if actually you don't have good functions, good model from the beginning. That is here something in red that will have a small error. So actually, I don't like the conception that, I mean, I wrote this slide because someone someday like told me, okay, machine learning is not science, it's prediction, and science is modelization. And I don't like to oppose both, actually. I just think that they are kind of complementary. So this was just inspired by the definition of regret, but maybe it's nothing to do with what we want to do now. So because of this, I will now go to the second part of the talk. So actually, maybe just to explain the structure of what will come from now. I will start with these bounds in square root of t for randomized strategy. So in some sense, I will give you the universal strategy that works more or less all the time. It's a kind of strategy that is like nice in almost any context. It will behave well, so it seems nice, and you will have the general results. Okay, and then I will try to give some refinements. So I will try to give some refinements, on how to use instead a deterministic strategy if you don't like to draw to sample, if you don't like to use random things. I will provide examples. I will try to propose strategies based on gradients that are also deterministic and not stochastic. And in the end, try to make some connections with MT's lectures yesterday, so with variational inference. But the kind of basic idea, you will get it just from the next few slides by this strategy, exponential weighted aggregation. Okay, so I will once again, to present the exponentially weighted aggregation, start with a finite set of predictors, and then at the end of the section, I will extend it to any set of predictors, finite, infinite, whatever, continuous or not, etc. But for now, I will start with a finite set of predictors, but I don't assume anymore that one of them is correct. So I think it's a kind of more realistic setting, okay? And what are these predictors? I just want you to feel free to imagine absolutely anything, because actually the theorem I'm going to state in a few minutes is going to be valid if you use statistical predictors, which means that, for example, at time t, you consider all the data you had before, x1, y1 to xt minus 1, yt minus 1, xt. And actually, you use them to train, for example, a least square estimators, and then you multiply this least square estimator by xt. So you can use a statistical model, use it to prediction, and this will be my function f1. Okay, and you can use another model like ridge regression, function f2. Okay, so you can use any model you want and use it to build a predictor. And this is what I mean by a predictor, any function that depends on the past of the data. But the point is, actually, the example I showed you with the like football guys before is important in the sense that this theorem works. The theorem I'm going to show you just in a few minutes works even actually if your experts, you don't know what is within them actually. So in some sense, if your predictors are given by an expert on TV that says next year the economic is going to be this, and you don't know what model this person is using. And you might think, okay, if I don't know the model that this person is using, then maybe I don't want to rely on it. But on the other hand, if this person is always right, then maybe you need to use the advice of this person. So actually it's possible to mix. And from now, I will assume that actually the predictions that I will denote by yt at 1 to yt at m can be of both types. They can be controlled by yourself actually and just be like, come from statistical model. Or they can be a prediction made by someone else and you don't know if you can rely on this person or not. Okay, so in order to make no distinction, I will write them all like that, not without any reference to the function f, but some of them can correspond to a function f, and some of them can correspond to like black box experts. Okay, and how to choose at each step a yt at, so that actually I will have a small regret and note that in this case there are only m predictors. The inf in the regret is actually a minimum and it's reached for one of the experts, even though I don't know which one. So now is the strategy that I propose, and it's called aggregation because actually I will propose an aggregated version in the next slides, but I will start with a randomized version actually. So you start with weights for each expert. And honestly, if you don't have any idea, you can take, for example, the uniform distribution. So you give a weight 1 over m to each expert. Okay. And then at each step, you draw an expert randomly. So IT will be the index of the predictor that you choose. Okay, so you draw it accordingly to the current distribution PT of I. Okay, so PT of I is the probability that you sample expert I. Okay, you predict according to this expert. And then, of course, you see the truth and you know, oh, this expert was right, this expert was wrong. But exactly as I told you like a few minutes ago, no expert is always right. So when an expert makes a mistake, you don't want to remove it forever, but instead what you want to do is to penalize it probably. So the proposition here is to keep the previous weight, but to multiply by e to the minus eta, learning rate, times the loss of the expert I. Okay, so in case the expert make no mistake, then actually you don't change PT of I, but in case where the expert makes a huge mistake, then actually you will decrease the weight of the expert a lot. Okay, the problem is that if you play with probabilities like that, well, they no longer probability in the sense that the sum might not be any longer equal to 1. So after multiplying by exponential of minus the loss, you have to renormalize this so that you obtain a new probability distribution, PT plus 1 of I. And you iterate. Next, you will draw the expert IT plus 1 from this new probability distribution. You make the corresponding prediction and you update. Okay, is it clear how I mean, I'm not asking if it's clear why this strategy would work all the time, but is the way you would, for example, implement this strategy in practice clear? Like, did you understand correctly the definition?
How to choose initial weights?
So, good question. The initial weights, if you don't have any information at all, you should choose something uniform, 1 over m to 1 over m. Okay, the uniform distribution. It's not the only possible choice. The point is that actually I will state a result on the performance of this strategy, and the result depends on the initial weights, actually. So maybe it will be clear probably just in 1 minute, actually. So if you use, oh sorry, actually I forgot to write this, but if you use uniform weights, okay, then actually when you have a bounded loss, okay, so bounded loss, for example, in classification, the loss is in 0, 1, so capital C will be 1. Then the expectation of the regret will be smaller than eta, the step, times C squared times T, times the constant, plus the log of M over eta. Okay, and actually, it means that if you know that you're going to play this game for example, 1,000 steps, so t equal to 1000, then you should try to optimize actually this bound with respect to eta. And the minimizer with respect to eta, well, I just like differentiated this, the second, like the right-hand side here with respect to eta. You find that it is exactly this. It is in square root of log m over t, but in this case, you end up with a regret bound that is a constant times square root of t log m over 2. Okay, so you have a regret in square root of t, which is actually much better than something in t that you would have using naive strategy. Now, to answer your question, if you imagine that you don't take uniform weights, p1 equal to p2 equal to etc. equal to p of n equal to 1 over n, then actually here, what you would have is the log, instead of m, you would have the log of 1 over pi, where I is the best expert. Okay? So it means that in some sense, if you have some hints that the first expert is the best one, then of course you should start by giving more weight here, because it would make 1 over the weight smaller here. But on the other hand, if you don't have any hint on which one is the best one, then actually the only way to try to keep this bound reasonably small for all of them is just to take all the initial weights equal. Okay, so this is, yes, sorry, I interrupted you actually.
There is the question if an expert that is faulty, so to say, can it be trusted again?
Mm-hmm. So the point is, you see here that if the experts make a mistake, then its vote will be reduced. It will be multiplied by e to the minus the loss. So especially in the case where the loss is not just 0, 1, but you can have small loss for small errors and big losses for big errors, then if an expert makes a huge loss, then its weight will become almost equal to 0. But actually, the point is, what will happen next? It will depend actually on the behavior of the expert next. Because if actually then it starts to perform better again, then it might be that little by little the weight increase again, actually. And I will show you an example in a few minutes. Okay, so this is the difference where the situation where you knew that one of the experts was right. If no expert is always right, then in some sense, even the best one can make a mistake. So you can decrease its weight, but you should not remove it forever, because if it's the best one, then it would be stupid to remove it forever. Okay.
So we always choose randomly the guess of an expert at each time step and do not try somehow to aggregate the guesses of experts for a single guess?
Exactly. So I will actually show you in 1 minute that if the loss function is convex, then you should aggregate them instead. So this is just a result that will come in 1 minute. So just one remark, the expectation of the regret here is not taken with respect to the data, it's just taken with respect to your own randomization, okay? So with the vote that you, sorry, with the experts that you draw randomly. And also I want to say that in case, because here, when I optimize with respect to eta, actually I optimize with respect to eta by knowing capital T, which means that in some sense, I know that I will have to predict during 1000 rounds, but I optimize eta to optimize well during 1000 rounds. And then what happens next, I don't really care. In practice, if you don't know how long will be the game, it's possible actually to replace here, sorry, eta in 1 over square root of capital T by 1 over square root of T, and you obtain similar guarantees. It's just that the term here is a bit more complicated, but the order of magnitude is the same. And now I will answer your question actually in the next slide. What if you don't want to draw experts randomly, but you want deterministic predictions? So I propose the same strategy. First, weights, and then you update weights in the same way, but you predict YT at being actually the sum of the expectation, sorry, of the experts drawn from PT. So actually you just make them vote, but you make them vote by giving them the weight PT. Okay. It appears that actually it's not always sensible to do so. Like, if the loss function, sorry, if you are doing classification, okay, so yt is equal to 0 or 1, then actually your votes of 0 and 1s will be somewhere in between. Okay, so it will be something like 0.4. Maybe it makes sense. Okay, is this number 8 or a 6? Well, I'm just saying 0.4 probability that it's a 6. Okay, you can accept for prediction. Now, if the classes are A, B, C, D, how can you make vote A, B, C, D? It's not meaningful. Okay, there's just no meaning for this. And actually, the point is that this algorithm cannot always be used. In some sense, actually, it will make sense only if the set of hypotheses you accept to consider is convex. Okay, 0, 1s. Okay, well, I take the convex set between 0, 1, so the whole interval 0, 1. If I'm allowed to make prediction in this interval, then it's fine. Otherwise, it's not the case. And actually, the point is that in this case, you have a bound on the regret. That is no longer an expectation, it's a deterministic bound, but it's also only if the loss L is convex. And the bound is completely the same. So it's eta c squared t over 8 plus log m over eta. Okay, so exactly in the same way, you can optimize it by choosing the adequate eta, and you obtain this. That is that in this case, you will propose an aggregated strategy. So you make the experts vote, and you predict as well as the best possible expert plus something in square root of t log m over 2. Okay? I just wanted to state the result because, as I said, it's not very nice to choose eta that depends on a given capital T, because in this case, it means that your regret can be low until capital T, but then it can increase again. So if you want to choose a eta that do not depend on when you will assess the algorithm, you can just actually state here, instead take eta t that depends in the small index t here, and actually you will get the same bound plus a constant term and multiplying it by a factor 2. Okay, so I didn't want to insist too much on it, but it is actually possible to do so. Okay, for now, that's it for the theory of EWA. I did not plan to, even though the proof is quite simple actually, but I did not plan to prove these results and rather to focus on examples. I hope you're not too frustrated about it. Otherwise, maybe I can actually, well, anyway, the books I provided as references give versions of the proof, and it's quite elementary actually. It relies really on elementary tools, so you should look at it if you're interested in it. But I want to show some real life examples maybe. So is it okay now if I switch to quickly before the break to a real life example?
We can have a real life example and then the break, no problem.
Hmm?
We can have first the example and then the break, or the break and then the example, as you prefer.
I think that the examples are not too tiring, so maybe we can do like the examples fast. It's just to show you like some real life example. I will not dig into details. I just want to. It's more like an advertisement actually for the method. This is Gilles Stolz. He's one of my colleagues in France actually. You might know him because a few years ago, like he was giving a lot of tutorials on online learning, and now probably like he's very busy with his family, so he travels less. But he taught me actually everything I know about this theory, and he wrote a paper in French here actually, but there is a version in English in another paper on the archive actually. And the point, he was actually asked by people working for I don't know actually, it was for the government or for a company owned by the government. But anyway, they wanted predictions about the air quality in Paris. And the idea is that they just had data from many stations. These stations actually would be meteo stations, like taking temperature, the direction of the wind, the strength of the wind, but also like the quality of the air, and especially the ozone concentration. So the point is that ozone, it's good when it's high in the sky, but actually when you breathe some ozone, it's quite toxic for you. And it appears that the ozone concentration is between like this value, 40 microgram per cube meter, and like 2 or 3 times this value but it's due to cars and to industry around you that produce a lot of ozone. And the point is that if it becomes too high, then it's not good for your health, actually. So the point is that they want to predict when it's going to be high or not. And they asked physicists and geophysicists and engineers, well, can you propose a model? And each proposed a model that was sensible, using meteorological variables, using chemical modeling, like modelization of the atmosphere, the movement of the air, etc. So a lot of PDEs. It was quite complicated, and in the end, it's very expensive to compute the prediction of one expert. But still, they had 48 experts, and each of them seemed sensible. And I want to show you what an expert would predict. So this is just one day at midnight. They will predict the total ozone in the next day, but hour per hour. So actually, you see that it highly depends on the time, and it's quite normal because actually at 5 in the morning, there is no pollution. And then suddenly at 7 or 8, that was before COVID actually. So everybody was still working, not at home at that time. I don't know if you remember that. But then like still people would take their car at 7 and go to their company. So there was a lot of pollution, and then the industries would start to work. So that's a lot of pollution, and suddenly in the evening people stop and they go back home and watch TV, and they stop using their cars, and they stop, like the industries shut down, and again no pollution. So it looks like a typical profile for a day. The point is that all the models seems reasonable. They all predict the same thing, like they all look the same. It's the same wave. But on the other hand, look at like the orange model here and the green model here. This one predicts 40 at 5 in the morning, and this one predicts 80. So like there is a wide range of predictions. And over 1 or 2 years, they used like the exponentially weighted aggregation to try to predict as well as the best expert. And this is just what I want to report. It's not a lot, but actually the best expert was doing a mean squared error. So they were using the quadratic loss in this case. The quadratic loss was of the order of 22. And actually EWA, in this case, the exponentially weighted aggregation strategy, was not only doing as well as the best expert, but even slightly improving on it, okay? Which means that actually, in some cases, just to aggregate things can even improve on the best of them, okay? Just to compare, a uniform mean of the experts would be doing worse actually than the best experts, as expected. So it's quite important, and actually the results were used in practice because all these models, once again, make sense from a physical point of view. So you don't want to erase them, you want to keep them. But then still it's nice if you want to return a single number to predict what will happen the next day. So you have something to give to politicians that they can talk about on TV for the next day that is very short, very simple to explain to people on TV. You can return just a number, and actually if you use the prediction made by EWA, it relies on all the models, and it's actually improving on them, okay? And when you do so, usually what people tend to say is, well, sorry, but actually we can guess what is happening, okay? We can guess that actually here, there is one model that is better than the others, and its weight will become equal to 1, and all the other ones will become equal to 0. So actually, there's no point in using this strategy. Maybe it's good in the beginning, but after a few steps, you will end up with just one model that is the best one. And I just want to show you that it's not always the case. And in this paper, they plot actually the weights of the experts. And it's very important to see that most of the experts have weights almost equal to 0, but it's not only one of them that has a weight that is significantly different from 0. It's 4 of them, and moreover, it changes with time. So in the beginning, between day 1 and 30, it's first this orange one and here this pink one. So maybe you don't really see it, but the first spike here and the second one are not exactly the same color. One of them is orange and the other one is kind of pink-red, okay? And then these experts disappear, and 2 models become very important for prediction. It's the blue one here and the green one. But both of them have weights that move slightly, so they are probably quite similar. But actually, if you use these 2 experts and not only one of them, you do better than the best of them in the end. So it's quite important to see that this strategy is not as trivial as it might look. Okay. I talked too much, I'm sorry about that. So I was a bit slow. So maybe I just want to mention that there is another example that I covered myself with a PhD student on economics. So using data from INSEE, which as far as I know from Wikipedia must be the same than this institution in Russia. So actually it's the National Office of Statistics in France. And we tried to use data from INSEE to predict actually the GDP growth since 2000. And we obtained similarly good results. But maybe as I don't have a lot to say about this example, I should skip it. So we should take the break and I will carry on with the theory after the break. Unless you have some questions now, I'm happy to answer questions. I mentioned it actually in the beginning, is that sometimes you have an infinite family of predictors and not a finite family of predictors. And in this case, I mean, you can start to think about either statistical models, parameterized set of predictors like linear predictors, or even actually we'll switch to this a bit later, but you can start to think maybe about neural networks, and theta would be the set of all the weights on the different layers, and you want to try to find what is the best possible weight to give to each neuron, and etc. Okay. So if you have an infinite family of predictors, it turns out that the analysis of EWA can still be carried, and actually you can just write it down again, actually. Still choose your learning rate, eta, and you choose a prior distribution on the weight, but this time if the set is infinite, then actually it might be, for example, a continuous probability distribution. It can be a Gaussian distribution or something, okay? And then actually what you would do is that you would make the different predictors vote according to a distribution PT. And then at the next step, you update PT to PT plus 1 by, here again, multiplying the distribution PT of d theta by e to the minus the loss. Okay, so basically, you can just think of it formally as I copied and pasted the previous slides, but I replaced sum by integrals, which is usually what you do when you moved from a finite case to a continuous case or to a general case, because actually this measure P can be discrete or continuous. But I think now that if you know some statistics, and I'm sure you do, then actually this thing here and this terminology prior should ring a bell, actually. It looks like Bayesian statistics. And this is something I would like to mention. So I will, okay, actually I will first state the theoretical results, and we will write down actually properly a connection with Bayesian statistics later. In this case, actually, it turns out that there is still a regret bound that can be written. The sum of your losses is smallest than the smallest possible expectation of the sum of losses under any probability distribution P, but it is penalized by the Kullback divergence between P and pi. Okay. This result might look a bit abstract, but it turns out that in the case where actually pi is a uniform distribution on the finite set, it becomes exactly the result I wrote previously for EWA. The Kullback divergence, I just remind the definition here if you probably know it, but so it's the integral of the log of the density of P with respect to the prior pi times the distribution P, okay? And it's infinite if P don't have a density with respect to pi, okay? And the point is that it appears that when pi is uniform on 1 to m, if you choose P as a Dirac mass on one of the I 1 to m, actually, then the Kullback between P and pi, you can just write it down, it's just a one-line derivation. It is exactly equal to the log of m. So actually, it means that the special case I gave before can be seen as the special case of this general result, okay? But more importantly than this result that is a bit abstract, and I would comment and explain how to derive other regret bound from this if we had like 2 or 3 more hours, but you'd get bored of it actually, so don't regret it. But instead, actually, I just want to comment on the form of this, because I told you it looks like Bayesian statistics. Okay, look at it. Pt plus 1 is e to the minus the loss at time t times pt. But there is a recursion here. Pt is e to the minus the loss at time t minus 1 times pt minus 1, and so on. And in the end, you end up with pt that is the product of the e of the minus the loss function at time I ranges between 1 and t, times pi, that was the initial weights distribution, that is the prior, okay? And it turns out that actually this can be interpreted as a Bayesian estimator, so that is as a posterior in a statistical model. For example, if you're in a regression problem, if xt is deterministic, yi actually is centered at f theta star of xt and with a variance sigma star, okay? Then when you take eta equal to 1 here, and you take L being equal to the log likelihood, that is y minus y prime squared over 2 sigma squared, then actually the likelihood of the parameter theta becomes exactly equal to the product of E minus eta times the loss, exactly as here. Which means that in this case, it's important to understand that Pt plus 1, the weights that we have at time t plus 1, is proportional to the log likelihood times the prior, that is to what we usually call in Bayesian statistics, the posterior distribution. Okay, so in some sense, even though the context is not the same because we're not dealing with IID observation, until now there was no statistical model on the data. But if suddenly you decide to choose a statistical model and to assume that the data come from the statistical model, then suddenly, actually, EWA boils down to the posterior distribution in Bayesian statistics. Okay, so it's a kind of generalization of the posterior. Just a few remarks. In Bayesian statistics, I say, like, if you want to recover Bayesian statistics as a special case, you take eta equal to 1. Okay, and here, what did I say? I said somewhere, probably, I wrote at some point, eta is in 1 over square root of t, sample size. So it means that eta is much smaller. Eta goes to 0, actually. And in Bayesian statistics, people take eta equal to 1. So there is an interpretation to this fact, actually. It is that if you know that the model is right, then it's okay to take it eta equal to 1. If the model might not be correct, actually, when you're dealing with sequence of objects and labels, xt and yt, then actually random fluctuation can be quite huge, and you cannot trust the posterior distribution anymore. And actually, by taking eta smaller than 1, you reduce the oscillations of the posterior distribution. You transform it into a function that is more stable, and it appears that in this case it still works even when the data is not generated from any model that you would decide in advance. Okay, so in some sense it's nice. It provides an extension of Bayesian statistics. Okay, that's more or less everything I wanted to tell you about strategies based on exponentially weighted aggregation. So I will probably not cover everything, but I want to talk to you about the online gradient strategy. Still, now, if you have any remaining question about EWA, I think now is the right time.
No questions, we can continue.
No questions, okay. So I will now propose a strategy that will be probably more practical in the infinite case. I did not insist too much actually on EWA in the infinite case, because actually what happens in this case is that to compute this integral here is usually a very difficult problem. Okay, so when you have the set of experts, like the set of 80 physical models to predict the pollution in Paris, well, okay, nice. You can just make a sum with 80 terms. It's not very computationally expensive. Now, when theta ranges over an infinite set, then usually people use Monte Carlo methods to compute these integrals. But if you have to do it online for high frequency predictions, like for example, in finance, you would have to predict things like 1,000 times per second. And in this case, it's too slow. You just cannot do it. So I would like to propose to you a strategy, and actually it's something that you already know, but you will see that it's possible to connect this thing that you already know to online prediction. I will propose a strategy that works well for infinite predictor sets when they have some structure. So I come back here to the setting where I want to predict y1 from x1 by y1 at, etc., and then I iterate. But this time I will focus on the case where actually I have a set of predictors I don't assume it's true. I wrote model, maybe I was wrong to write model because I don't assume it's true. It's just a possible set of predictors. But it's not finite anymore. It's infinite. I want to predict yt by a theta t times xt, but theta t can be any theta in r to the d, say, for example. Okay, and more generally, actually, what I will discuss now, it would be valid for any function that depends on the parameter and of the input xt. The online gradient strategy would consist just in starting from an initial value, theta1, and then actually we will iterate actually to try to guess the best possible parameter theta here for predictions at time t. But we have some assumptions on g actually, so we will require that the function g is convex in theta and that the loss L is convex with respect to y. Okay, and in this case, the strategy is as follows. So at time t, I have a theta t, I receive a new object xt, and I predict yt by yt at, which will be simply g of theta t of xt. And then the true yt is revealed, so I suffer the loss L of yt at yt. And actually, then I want to update my parameter. And what I propose to do is just to update theta t plus 1 by theta t minus eta times the gradient. So sorry, I wrote like this, the gradient. I don't know if it's the notation you're used to or not. So this is the gradient of the loss of g of theta and xt and yt with, sorry, with respect to theta. Okay, so it's just a gradient update. The only thing that is quite important here to note is that we don't have to store all the past data because at time t, the update to transform theta t to theta t plus 1 only depends on the current data. Okay, so I assume that you have probably met this algorithm many times under the name like stochastic gradient, because very often when you want to train a large model like a neural network on a huge data set, you cannot compute the gradient at each step with respect to all the data. So you just take some of them randomly and you compute the gradient with respect to these randomly selected data. Here, it's extremely similar, but the idea is not the same. It's not to train something on a whole data set, it's to do online prediction. Because here, actually, if you follow this step, then you can use theta t to predict yt plus 1 from xt plus 1. Okay, and actually, exactly in a similar way, you can prove actually the following regret bound. So the bound is as follows. It tells you that the sum of the mistake that you will make by using this strategy will be as small as possible, as will be like the smallest possible balance in some sense between the loss of g of theta and xt with respect to yt, okay, paying a price that will be the norm of theta squared over 2 eta plus a term in eta tl squared. What does this mean? This means that actually, if you choose, in some sense, if you're confident enough that there is a small parameter theta that will, like with a small norm b, that will do good predictions, then you can restrict the infimum above to the set of theta that has a norm smaller than b. And actually, in this case, you obtain something quite explicit. You can optimize with respect to eta again. And you know that you predict as well as the best parameter theta with a reasonable norm plus bl times square root of t. So here again, it's a regret in square root of t. Okay. So maybe there are many things here. First, once again, I apologize that I did not write the proof in the slides. Maybe you expected more proofs. I presented 2 books in the beginning. The book by Shalev-Schwartz is quite short and contains a very detailed proof of these results. So if you're interested in theoretical results, I really ensure you like just read it. It's very nice to read, very easy to follow, and even though it's complex ideas, but it's easy to follow. Second point, if I recap, it's once again a bound in square root of t, which is as I promised from the beginning. Remember, I told you, like the big picture, you can always find a regret bound in square root of t using a randomized strategy. But if you want a deterministic strategy, and this strategy here is deterministic, okay, it does not depend on some random sampling, you can still have a bound in square root of t, but this bound will be conditional on some assumptions. And here the assumption is that the loss is convex. Okay, and Lipschitz. Okay, so what's next? I can't remember what's the next slide. Oh yeah, it's a very, very, very toy example. This one is not a real life example at all. It's just a data set that I found for an example for some students just a few weeks ago, actually. So it's just like a data set that is on the machine learning repository, and it appears that actually this is a data set where people were asked to classify type of glass, okay, according to the chemical composition of this glass. And actually, this dataset was actually produced by the police because they wanted to use it for criminal cases. You know, like just in some like detective story where sometimes the characters, like the policeman asks the guy, like, did you kill your wife? And the guy says, well, I did not. But, well, you know, your wife was killed by being thrown out of a window, and there is some glass on your jacket. And the guy say, yeah, but the glass on my jacket is not the glass from a window. It is the glass from my car because, like, the glass of my car is broken. And the policeman say, here's the glass on the jacket of this guy. The glass from a window or the glass from the car? So actually, it sounds like a stupid detective story on TV, but it's true. Actually, this dataset was produced for this reason. And in the end, actually, just using logistic regression and the stochastic gradient algorithm, just like here, I just plot how the regret would evolve. That is the number of mistakes that I make. And here, that the number of mistakes that would make a stupid strategy that would reply +1 or -1 randomly. And actually, it's interesting to see that using this gradient algorithm, you converge to what is the optimal about for these data sets. That is 20% of mistakes and 80% of good strategies, while actually the random strategy would converge to 50%. So I'm sorry, this one is a very toy-ish example. It's not at all a real-life example. But the reason why I show it is just to show that actually it can be implemented just in a few lines. So if you're interested, like once again, I can just share the Python code for this, which is, I think, 5 lines. It's no more than this. So okay, quite easy to implement. Is it something you're familiar with, this online gradient algorithm, or?
We have some questions. So it
Yes.
says, is an updating theta at each step on single instance very noisy when we risk forgetting information?
Mm-hmm. So, sorry, can you say again? I mean, it's like I hear that what's the problem is that if it's very noisy, the update?
So we are updating theta at each step on a single instance. And isn't this very noisy? Are we losing information by doing this update at each step?
The answer is surprisingly not so much. Okay. The point is that if the instances are all very noisy, then in the end, it means that there is no good predictor in some sense, okay? Which means that here the infimum will be large anyway, okay? Now, the point is that here, the regret bound is always in square root of t. And you can't improve it, actually, basically. The idea is that even if instead of using data 1 by 1, you decide to store them and use them 2 by 2, 3 by 3, or even to use all the data from the beginning, you will make the algorithm more complex. You can make it slightly more accurate, but you cannot improve on the order of magnitude of the bound with respect to t. You cannot improve in general on the square root of capital T. So it's surprising, but actually, no, you cannot improve so much by, I mean, you're not hurt so much by the fact that the data is noisy. If the data is noisy, very noisy, any method will perform badly, essentially because of this term. And this term is kind of incompressible anyway.
There is another question that says, what kind of models are we talking about? The loss is often non-convex for complex models.
Sorry, maybe I miss something. What you call what do you call the model actually here? The way I decided to model online prediction, or the function G actually?
Let's see what the person writes. But meanwhile, there is another question: is how can we derive the link function? Oh. So going back to the original question. So
yeah, sorry.
The models that we're talking about, so the person says that the model for this person is something with weights, for example, like a neural network.
Okay, so indeed, here, if you want to train a linear function like this, then actually this is nicely linear, and you will satisfy actually that if you take L as the least square or least absolute value, then actually this will this function will be convex. Of course, if you're using a neural network here, the point is that this algorithm is popular to train neural network, but in the end, it's true that in this case, you would not satisfy the assumption of the theorem that I gave, in the sense that this here, the composed function L of G of theta will no longer be convex with respect to theta. And it is what is important if you want to prove this result. So I should have mentioned it actually, I acknowledge. This would work for simple models actually. And the reason why it works for more complex models like neural network is not captured by this theorem, even though it works in some situations, but it's not captured by this theorem.
All right, so we can continue. We have about 10 minutes left, and also we have other questions that we have collected previously. So
10 minutes more and then questions?
Yes, exactly.
Okay, so actually I want to end up by presenting something that will make a connection with MT's talk that you've probably seen yesterday. So MT is interested in training a neural network with Bayesian principles. He's actually the head of the team I'm working in now since a few months. And also on the left, my former PhD student, Badreddin Sherif Abdelatif. And everything I'm going to present now is from a paper that we both, we wrote the three of us together for ACML last year. And MT is interested in using these methods for neural network, even though what I will present once again will be valid for convex losses, and so will mostly be usable for simpler models. But the point is, in some sense, I will not have time probably to present all the details, but I just want to present the main idea. Main idea is that I said on the one hand, we have exponentially weighted aggregation, which is close to being a Bayesian method. Okay, and Bayesian methods are quite popular because they don't only return a prediction, they don't just return a theta t. Okay, they don't say use theta t equal to this to make the prediction, but instead they provide you a probability distribution on theta, which means that actually they quantify the uncertainty on theta. They will give you a theta that is the most likely, but they will tell you theta might actually be in this set or this set, so you can interpret it like confidence intervals on the parameter theta. Okay. But I say it's computationally not feasible. And on the other hand, we have this very nice online gradient algorithm that is computationally feasible because at each step, you just have to compute the gradients with respect to this. And as long as you can compute these gradients, then you can implement this algorithm. Okay. And the question is it possible to get a Bayesian method that would be as efficient as this algorithm in practice? Like as easy to implement? And the answer is yes, but actually MT probably proposed you such methods, and I'm going to propose a simpler version in some sense because we wanted to analyze it theoretically to provide a regret bound, and we had to start it by a toy version to start it with. But I want to explain briefly the idea. The idea is that if you consider this EWA distribution here, that is the generalized Bayes rule in some sense, then actually it can be reached. It turns out that actually it is equal to the minimizer of this problem, the minimizer of the sum of the expected losses that you observed until now, plus the callback between P and pi, pi being the prior here. Okay, and the whole idea of trying to make Bayes feasible is to start with the fact that this minimizer here is done over any probability distribution P, can be any probability distribution, continuous, discrete, etc. It's an infinite dimensional set. It's a huge set, and you cannot deal with it in practice. So instead, actually, you use the ideas of variational Bayes that MT presented yesterday, and Tamara Broderick will talk about it, I think, today or tomorrow, I don't know, but she will present similar ideas. And the idea is to restrict P so that it belongs to a finite dimensional set. Okay, so you choose a family of probability distributions, Q mu. Say, for example, mu is m sigma squared, and Q mu is the Gaussian with mean mu and variance sigma squared. And you decide to approximate the posterior by a member of the family Q mu at time t, so it will be Q mu t. Okay. Of course, you could from the beginning decide to use an online gradient algorithm on the expected loss. So it would be something that would be in between Bayesian and online gradient. It turns out that actually it works, but it's not the best thing to do in practice. There are ways to improve on it and to propose something that makes more sense from a Bayesian point of view. And the idea is as follows. Actually, we have to understand the Bayesian, the online gradient step from another point of view. Just for short, first, look at the gradient term here, the gradient with respect to the loss, with respect to f theta of xt and yt. I decide now to write it for short because it's always, it depends on f, it depends on theta, xt, yt, etc. But the xt and the yt never change. I'm always focusing only on theta. So I will rewrite it in a shorter way as lt of theta t. It's the loss of the predictor t at time t. Okay, and the point is that the gradient step, this one here, can be obtained by the following minimization programs. Okay, if you minimize like this, the scalar product between theta and the sum of the gradients that you've seen so far, plus the absolute, the norm between theta and the very first value of your optimization algorithm. Actually, well, just try to minimize this function, you differentiate it, this will become only the sum of the gradients, this will become a linear term, and in just one step, one line, you will obtain this recursive update. And exactly the same for this program here, when actually you just minimize the scalar product between theta and the previous loss, plus the norm between theta and the previous parameter theta. So in some sense, you can interpret this as something that will say, okay, you want to find theta, you have to find the direction that corresponds to the gradient of the previous steps, and you want to go very far in this direction, but not too far because you don't want to make this penalty term explode here. Okay, but now if we come back to Bayes, as I said, actually Bayes can be interpreted by minimizing here in the same way a data fit term plus a penalty term, but the penalty term is a Kullback distribution. It's not a norm. So actually, based on this, it seems natural actually to propose a kind of adaptation of the following, of the previous like updates for the gradient step. Once again, the gradient step in a sophisticated way can be written like that. And actually we proposed, if you want to work with a Bayesian setting, to minimize like the distance, the scalar product between mu and the expected losses, the gradient of the expected losses that you've seen so far, plus a penalty, but the penalty will be the KL between Q and pi. Okay, and you can do the same for the second form here of the online gradient. And something appears here is that here these two equations will give you the same solution, that is the online gradient algorithm. And in the Bayesian version, we end up with two algorithms, and they turn out not to be equivalent, actually, in the sense that, sorry, it's a bit heavy, but you can check the calculations line by line, and actually the updates are not exactly the same in practice. So here, I just said, for example, I start from a prior distribution that is a Gaussian with a fixed variance. And I want to find the best approximation of the posterior as a Gaussian with a mean mu and a standard deviation sigma. And the updates are given by the following formula, which they are kind of ugly. And if you have to implement them, you have to look at them. Otherwise, it's not really important to try to implement them. But what is important is to see that they are not exactly the same. So we had here two propositions to extend base. Well, sorry, not to extend base, actually to, I'm gonna say, to modify slightly base so that it becomes something fusible that looks like an online gradient, but instead of returning a single value, we return a probability distribution. And the probability distribution here is Gaussian, and we know how to update the parameters. So the point, more or less, is that you can propose, maybe you can say like, hey, okay, you can propose any algorithm you want, whatever, does it work or not? And this is the point, is that this algorithm, for example, the first one here that we called SVA, Sequential Variational Approximation, okay, we were able to derive a regret bound that is quite interesting because actually, if you look at its form, like it's a sum of expectations plus the callback between the current distribution and pi over eta. The form of this is actually exactly the same as you have for EWA. But the point is that it's no longer EWA, it's no longer the true Bayesian estimator, it is the variational approximation that is computed by an online gradient algorithm, slightly modified, okay? So in some sense, we managed to find a way to modify base so that it becomes computable online, but it still satisfies the same theorem, okay? And in particular, we made some explicit calculations. So maybe this is the part that is a bit mysterious, and I could explain this part, sorry, with a bit more details if I had a bit more time. But like, if you're interested in the detail, don't hesitate to ask me questions about it. Like computing this upper bound explicitly shows actually that we have a regret bound that is of the order of the dimension of the model times t. So it's still something in square root of t, actually. So it works. In terms of regret, it performs as well as the previous algorithms, but it has the form that we wanted to have, actually. That is like a Bayesian posterior. Okay, there is also an analysis of the second algorithm. I don't want to spend too much time on it. The only remark I would like to do before I stop, sorry, maybe I went a bit too far in the end, but I hope that I convinced you that the tools that I proposed to you in the beginning, like this kind of regret bounds to analyze EWA and to analyze the online gradient, can be extended to more sophisticated algorithm, including the algorithm that MT tried to explain to you yesterday on how he tries to train a neural network with Bayesian principles, okay? And that actually we try to understand these algorithms now, including this one, SVA, by such regret bounds. Still, the algorithm that MT proposed to you is slightly more sophisticated. And I can just explain to you why, actually, in one sentence or two before I stop. Here, the strategies I propose, SVA and SVB, are in blue and purple on the toy dataset. And the online gradient algorithm is in yellow. And the algorithm that MT proposed actually is in green. It's the best one. But the point is that it relies on a different parametrization. In some sense, when you parameterize a family of probability distribution, Q mu, you can always change the way you parameterize it. Will you parameterize by mean variance or by mean standard deviation or using the natural parameters? And not all the parameterizations satisfy our assumptions, because here again, if we want to have this bound, we need the convexity of the loss function, and it actually imposes you to parameterize the model in such a way that you have the convexity. And rather surprisingly, the parameterization proposed by MT in green here leads to a non-convex parameterization, but it performs better than the one that we had in our toy algorithm. So actually, it's the open question that will conclude this presentation. Actually, this is the algorithm proposed by MT. The open question is how to extend our findings to the parameterization proposed by MT, because actually his algorithm, I hope that he convinced you of this fact yesterday, are quite powerful and have very good results, but still right now we don't understand totally, at least in this online setting, why they perform so well. So we are on the way, but we don't have an exact understanding of this yet. Okay, so that's all I wanted to say. Thank you for your attention and for the invitation. Thank you.